And so live, I think from the beautiful campus of the Institute of Advanced Study in Princeton, New Jersey, we have Nima Arkani-Hamed, who will tell us about all-loop scattering as a counting problem.
All right. It's really wonderful to be able to be at this meeting, even if virtually. I'm very sorry, very sorry I couldn't make it in person. It's actually especially appropriate for me to talk about this general subject. It's a general subject I've worked on for about 15 years. But the specific things that I'm talking about today were really kickstarted by a very intensive semester I spent at the CMSA back in the fall of 2019. I have a tremendous affection for the place, and this work certainly would not have happened without all the opportunities we had for very stimulating collaboration that really started there and then really continued through the pandemic. And the first of a long series of papers on the subject have just started appearing this fall. So there are sort of largely two related bodies of work that I'm going to be talking about. A set of foundations for this new way of thinking about the very basic physics of elementary particle scattering process from a rather novel point of view. This is work with the wonderful young theoretical physicists Hadley Frost and Giulio Salvatore, and my good friends, the mathematicians Pierre-Guy Plamondon and Hugh Thomas. And that's been extended over the past year to really describe real theories that we see in the world around us when we look out the window. When I get to that part of the talk, that'll be work in progress with Song He in Beijing, my spectacular student Carolina Figueiredo, as well as Song's wonderful students Chu Cao and Jin Dong. Okay, so let's just get started. For the past 15 years or so, we've been asking the following question. We're interested in the very basic physics of elementary particle scattering processes, and we'd like to ask a reverse question. One of the earliest signs that there is something remarkable going on in the seeming very well understood basic physics is that when you actually compute the probability amplitudes for a couple of elementary particles in, they scatter in some way and they go out. There's a completely standard way of doing this calculation that involves summing over all the possible paths and trajectories the particles could have taken, each picture representing some particular space-time process. So this is a famous story of Feynman diagrams. And the entire purpose in life of this formalism, and it's really the purpose in life of the standard textbook formalism of quantum field theory, is to make the principles of locality of interactions in space-time manifest, and unitarity, quantum mechanical evolution in Hilbert space in a unitary fashion manifest. And that's wonderful, and those are the pillars of our understanding of fundamental physics handed to us from the early part of the 20th century. But there are interesting clues lying about all over the place that would take several talks to talk about in detail, but I'll talk about the one that's relevant for this talk. That making space-time and quantum and mechanics manifests is coming at a very heavy cost. For example, when you actually calculate the scattering process for even the very simplest process that are really needed to compare a theory and experiment at accelerators like the Large Hadron Collider, never mind processes that just happen in nature all the time. You have two particles come in, two particles come out. That's something you put on a problem set to test the graduate students. Two particles come in, three particles go out. That's already something that could be pages and pages of algebra. 2 and 4 out, hundreds of pages of algebra, thousands of pages of algebra. And yet, starting around 35 years ago, people started realizing that there was enormous cancellations that took place when you summed all these hundreds and thousands of pages of algebra, and the final answers were stunningly simpler than what you'd expect from each piece alone. And while 35 years ago, this was not universally recognized as the tip of a giant iceberg, today we know it's a tip of a giant iceberg. And it's an indication that there's a different way of thinking about this very basic physics, where these foundational principles of space-time and quantum mechanics will not be the stars of the show. Something else will be the star of the show. And what we've been trying to do for the past 15 years is discover what that something else might be. So we'd like to find a different question to which the amplitudes are the answer. The standard question to which the amplitudes are the answer are, You follow the particles in, and they evolve in Hilbert space. The wave function evolves in Hilbert space in some way. It's local and unitary evolution, space-time and quantum mechanics. But we'd like to find a different question, a question that sort of directly does not make any reference to these auxiliary structures like the interior of the space-time or the Hilbert space. A question that's directly formulated in just the kinematical space that specifies the data of the scattering process. And we'd like to find some kind of novel mathematical question to ask in that space whose answer are the amplitudes, and which gives rise to the amplitudes that we ordinarily, to the properties of amplitudes that we ordinarily ascribe to space-time and quantum mechanics. And in this way, give us some hint and some window into what the deeper ideas and more primitive mathematical structures might be that actually underlie space-time and quantum mechanics, which from many points of view is something that we're called to do here in the 21st century in fundamental physics. So again, the standard answer is local and unitary evolution of space-time, but we want to find a different question to which those amplitudes are the answer. And over the past 15 years, there's been an emerging picture. You know, if you think about what specifies the kinematics of a scattering process, the actual data that specifies this is very spare. There isn't much going on. You have to specify the n energies and the directions that the particles are moving. That's it. So roughly speaking, if you have n particles, you have to specify n3 vectors. And so in the space of n3 vectors, you have to somehow find a mathematical question whose answer is all the richness and complexity of the scattering amplitudes that we normally get from summing all these incredibly complicated Feynman diagrams. There doesn't seem to be much going on in the space of n3 vectors, or more generally, the space of that specifies the kinematic data. And I think that's been the zeroth order surprise of the past 15 years in this business, is that there's almost nothing in these spaces, but there's just barely a foothold enough to get enough of a structure that then builds on itself to actually lead to questions that do have all the richness and complexity to give us amplitudes. The emerging picture is that the basic structures are fundamentally combinatorial ones. It's not that surprising. There's not much left. When all you're talking about is a space of n3 vectors. There's essentially combinatorial structures in these very simple arid spaces, but they then get they get transmuted. There's geometric notions associated with this combinatorics, so things that have been called positive geometries, that then determine some analytic objects, differential forms that have canonical logarithmic singularities on the boundaries of these geometric spaces. And then integrating these forms gives us interesting polylogarithmic functions with the fascinating branch cut structure. And even summing some classes of these functions at all orders and perturbation theory gives some interesting window into what amplitudes could look like non-perturbatively and so on. And the kind of words associated with these ideas in this period of time, I think that the first hint for something like this was the story of the so-called amplituhedron for the scattering amplitudes of maximally supersymmetric gluons. And starting around 5 years ago, we started seeing these things in much simpler theories, much simpler, more basic theories, connecting to classic, famous objects in mathematics, the Stasha polytope or the isosahedron. Similar structures have been seen in cosmology. And what excites me about this entire endeavor is that it clearly describes the real world. The real world we see when we look outside the window again. That's the real world that I care about as a theoretical physicist, not, various toy models that we can spend decades studying. But ultimately, we care about that world that we see outside our window. The models that we're studying do describe the real world in some reasonable approximation. What I'll be talking about today in this talk is quite a bit closer to the real world than we've gotten before. What's been exposed in these investigations are some hidden symmetries and new mathematical structures and sort of pure magic in physics that's right under our noses. So that's what I want to give you a little bit of a sense for in the talk today. And I have a lot of slides here. I'm not going to go through them systematically, but I'm going to sort of pick and choose a few highlights to give you an idea of what's going on. All right, so let's begin by now talking about the simple theory that's going to be the star of the show for the first 2/3 of this talk. And this is the very, very simplest theory you could imagine of particles that carry color. So essentially, matrix models, except instead of doing Yang-Mills theory, we're just doing simple theory of scalars. So we have a scalar phi, it's an n by n matrix, and the Lagrangian is just trace phi squared. There's the trace d phi squared for the kinetic term and some coupling constant g times trace phi cubed. So as usual, we have the standard picture where we think of this n by n matrix as having an upstairs and a downstairs index. We have a famous double line notation, and so we can represent this cubic interaction by this graph, where on each side is sort of one of the each arrow here represents an upstairs and a downstairs index of this phi, and the trace phi cubed just contracts them in the manner that we see going around in this picture. So these are variously called double line notation graphs, Hooft diagrams, ribbon graphs in mathematics. We're going to call them fat graphs. And the Feynman diagrams that you get by summing these, by gluing these vertices together, look like fat graphs, exactly as we see. For example, for 4-point scattering, we'd have these two diagrams at leading order at so-called tree level, where we don't have any loops. And then we'd have corrections that involve internal loops, like these guys, one loop, two loops. These diagrams would be sort of planar. This would be a diagram that involves ribbons crossing and can't be drawn on a sphere, so it's a non-planar diagram, and so on. Okay, so there's a famous Hooft or large N expansion associated with this, and we're going to be talking about that expansion. Okay, so just to give you an idea of what it is now that we're going to be doing with this theory, we're going to be giving an expression for the amplitudes of this theory at any order in the topological expansion. So you specify the order of the topological expansion, there's going to be a formula for the amplitude, and the formula is going to be written as an integral over a space of a given dimensionality. The dimensionality is simply the number of internal propagators, or -1, depending on whether we projectivize the integral or not. That's a minor detail. Essentially, the number of internal propagators. As we'll review in a second, these are also pictures of these pictures define triangulations of surfaces in the standard way. So this is also the size of the integration is also the same as the dimension of the corresponding Teichmuller space associated with the surface. That's another way of talking about it. But what we're going to get is integrals over spaces of this dimensionality of very simple objects. So just to give you an idea, I've written down in this one slide all of the tree amplitudes and all of the one loop amplitudes in this theory. And they're all written, so this is written as an integral over an n-4 dimensional space, or really a projectivized version of an n-3 dimensional integral. This is over an n-1 dimensional space, projectivizing an n-dimensional integral. And you'll see that there are expressions, they fit on they fit on one page. But the interesting thing is that the functions that appear here have this interesting piecewise linear character to them. So these things like these xij simply represent what the external momenta are. We'll talk about them in more detail. The meat here is these interesting functions fij that look like max of 0, tj plus tj minus 1, and so on. So these are some interesting piecewise linear functions. And I've managed to write these expressions down on a single line. Each one of these objects, involves comparing, let's say, if I have n particles, order n objects to each other. And yet this is giving me, in effect, summing over exponentially many Feynman diagrams, which grow as 4 to the n at large n for these amplitudes. So something non-trivial is happening with these formulas, and I want to tell you where these formulas come from. All right, so let's just set some of the most basic context here. In thinking about the topological expansion, really we want to think about a single diagram, one diagram, which is not even a Feynman diagram. It's just telling us the way that the color indices, the way that the upstairs and downstairs indices of the phis are just contracted with each other. Well, there's a very standard way in which one of these pictures defines a triangulation of a surface. So every vertex defines a triangle of a triangulation. The roads of the associated with each vertex are the edges of the triangulation, and the propagators tell us the way that the triangulations are glued to each other. So these give us oriented surfaces. And so a single fact graph defines an oriented surface. It defines a triangulation of an oriented surface. So here's a sort of a standard case. If I have a disk with sort of 5 marked points on the outside, and I have this triangulation with 1, 3, and 1, 4, the internal chords 1, 3, and 1, 4 as I've drawn them, then first of all, I have this sort of a pizza slice triangulation. I can draw the dual of this triangulation and fatten it, and that gives me the picture of the associated fact graph. And the picture of the associated fact graph can also be thought of as just directly a picture of the surface itself, where I think about this region 1, 2, 3, 4, 5. If I imagine shading them in black, just like I did on the left, and shrinking them, then I go directly from the picture of the fact graph back to the picture of the surface. But just want to make a very, very small point, but an important one. Normally, physicists talk about the topological expansion in the language of summing over all the diagrams that can be drawn on a surface, or the topology of a surface, of a given surface. And here instead, we're going to think about a single diagram as defining the an orientable surface simply by giving a triangulation for it. So when we talk about what our kinematic space is and what's going to specify our scattering process and the order of perturbation theory that we're talking about, we have no choice but to give some triangulation of the surface. So one diagram is needed to even specify what we're talking about. But the entire rest of our life is going to live on that fact graph. It's going to live on that diagram. I'll occasionally switch back and forth to a picture of the surface, but really fundamentally, everything is going to be done in a world that's defined by a single fact graph, and questions that we can ask in that world that, as we'll see, will bring to life all Feynman diagrams, the reason for summing over all of them, essentially all space-time processes and the quantum mechanical edicts to sum over all of them with equal weight. These are all things that are going to come out in a somewhat magical way from simple questions we'll ask simply on that single world. Okay, so let me say a little bit more about how we think about the kinematic space. First, sort of informally, if I have any old surface here, then any sort of propagator, so a general Feynman diagram will correspond to a triangulation of the surface. And a triangulation is just a maximal set of non-intersecting curves that I can draw on the surface. So here's an example. So the propagators that we see in Feynman diagrams then correspond to the possible chords that I can draw on the surface. Again, here's a bunch of examples of chords that I can draw on a reasonably generic surface. All right. Now, if I want to be a little more specific, I should tell you Feynman diagrams assign momenta. They're not just pictures, they assign momenta to the curves. And so the momenta are also naturally assigned simply by imagining that I assign momenta to all the boundary components. And then any curve that I have, the momentum associated with that curve is determined by homology. So the momentum that is associated with this curve x here is the same as P1 plus P2 plus P3, because I can just smoothly deform x to the sum of the three components on the outside. Sometimes, like in this example, downstairs here, if you specify the momenta on the outside, it's not enough to determine all the momenta on the problem. That exactly occurs when there's loop variables. And so what you have to do in this case is simply pick a basis for the homology. So in this case, I can decide to choose this curve and give it a name, its momentum a name L. And then once I do that, everything else is determined again by a homology. So these other curves by the homology rule will be assigned momentum L plus P2, this one L plus P2 plus P3 plus Q1 plus Q2, and so on. Okay. Now already here, I want to flag a very important point, which is that there's a very big redundancy in this picture. I can draw, for example, here's a picture of an annulus just for fun with 2 points on the outside and 1 point on the inside. And here's a triangulation of the surface that corresponds to this fact graph. But here's another triangulation of the surface where I just take the inside part of the annulus and I rotate it some. So that's just doing a Dane twist. And this is an example of one of the simplest examples of the action of the mapping class group on the surface. Now, these are evidently different curves, but they correspond to exactly the same fact graph. And so where has the information gone? Well, one place that it's gone is that what we mean by the loop variables but loop momenta on the left and on the right are different from each other. The ones on the right where you shift some are related, but to the ones on the left by an overall shift in the loop momenta. In this case, summing over this momentum q of the internal part of the annulus. Now, since we're integrating over the loop momenta, this shift won't matter anyway, but already we see that we're going to have infinitely many copies. We're going to get infinitely many copies of the diagrams in this way of thinking about things. And so down the line, we're going to have to think about modding out by the mapping class group. Okay, finally, let's talk about how we would label in even more detail what the curves look like. So if we think about the kinematic space again, remember we're supposed to think about chords on the surface, but instead of thinking about chords, we're going to do something that's actually more natural from the perspective of the fact graph. It's something that in that professional surface people call laminations. So we're just going to call them curves. So instead of talking about the curve, instead of talking about the curve of the chord 2, 5, we imagine just pushing the endpoints a little bit. So we push the endpoints of 2 clockwise and 5 clockwise. Since the surfaces are orientable, this is always unambiguous. And so instead of going from 2 to 5, we go from a little bit to the right of 2 to a little bit to the right of 5. And so this is a little bit more natural because after all, we should really be thinking about these marked points as really not belonging to the surface or sort of holes. So instead, now we're drawing a curve that it really lives on the surface. And similarly, it's more natural on the left-hand side if I draw the corresponding fact graph that this just corresponds to some road that I can take, some route that I can take on the fact graph, starting on the road 2, 3, and then going to 1, 3 and 1, 4 and exiting in 5, 1. When there are punctures in the surface, and that means in the simplest case when the corresponding fact graphs have loops, like in this very simple example of a 4.1 loop diagram. Now, if we imagine drawing lamination, we sort of have trouble because it's not obvious where to exit. And so you simply don't exit. So the idea is that you come in and you just spiral around forever. And so these are called spiraling laminations, again in the professional surface literature, but we're just going to call them spirals. And of course, here's another case where now you can wind around some number of times. Now, if you have an additional sort of spigot on the outside here, this is now, of course, on the inside. This corresponds to the annulus. Then you can wind around some number of times before exiting. Okay, so all of these roads on the surface correspond to possible propagators that can show up in Feynman diagrams. And there's a very simple rule directly now in terms of the fact graph for reading off what the momenta are. This is just the homology rule. Just transcribing this homology rule trivially to the fact graph. You simply imagine assigning momenta to your parent base fact graph that defines the order of the topological expansion you're talking about, that defines the surface that you're talking about. You assign momenta to that graph, and then for any other graph, the rule is simply that the momenta, for any other curve, the momenta associated with that curve is a momentum at the start of the curve, and then you just follow the curve in, and every time it turns right, you sum all the momenta that enter from the vertex on the left to it. And so you can see that in all cases, the simple cases, in the spiraling cases, in all the cases, this rule correctly assigns the momenta that we would associate, we'd expect from the corresponding picture of the Feynman diagrams. All right, so that is now just introduced our kinematic space. Okay, so now just to make very clear, we want to talk about the order and some order in the topological expansion. I fixed some triangulation. I now for every road that I can take through this fact graph, I assign some momentum to that guy. I know what Feynman diagrams are. They just correspond to maximal collections of non-intersecting curves. But why should I even care about them? Who cares about summing over all collections of non-intersecting curves? Why should I sum over all of them? Why should I sum over all of them with equal weight? So these are some of the most basic questions that we have to ask if we now want to find a question. Our job now is to find a question to ask on this fact graph whose answer is going to give us amplitudes. And our 0th order challenge is to figure out why we would even care about the other diagrams and why we would care to sum them all with equal weight. And the answer to this question is lying in plain sight when we think concretely about what simply labeling the curves in the kinematic space. And I should say this part of the story really goes back to Thurston and in a little bit more detail, including boundaries and anyway, in more important detail to the story of surface cluster algebras, Feynman and Thurston and Fock and Goncharov from the mid 2000s, and we added, I think, just a little bit more to understanding some fine extra last details of this basic fact. But anyway, it's a very simple and beautiful fact, and I want to tell you what this fact is. But this is going to now be a gateway into a set of a different set of ideas. So once we understand what this picture is, it's going to give us new ways, of course, much more efficient ways of computing amplitudes with no reference to the diagrams at all. It's going to expose various hidden symmetries. This picture, which is fundamentally about particles, with the two-dimensional surface just being about the combinatorics of the topological expansion, also hands us the generalization from particle to string amplitudes in a very natural way, with no reference to a usual picture that things are fundamentally little loops and we have to quantize them and we have to have a worldsheet conformal field theory and vertex operators and all the rest of that. None of that's going to make an appearance. We're just going to directly land on the answer from a very different point of view, and actually from and using rather different variables. So if I have some more time, I'll explain what the connection between this way of thinking about string amplitudes and the standard one is. I probably won't have time to get to that. But in any case, there's a much more fundamentally combinatorial description of both particles and strings from this point of view. And I put strings in quotation marks because one of the interesting things is that we see that there's various levels of stringiness that we're allowed to talk about in this picture, and we can sort of control from the outside how stringy we want things to be. And we'll see exactly how much of the stringiness is needed for the practical purposes of describing this Trace Phi cube theory, describing more realistic theories like the theories for pions and for even Yang-Mills theory. And we'll see that we can get away with a tiny amount, a tiny frisson of the stringiness, much less than it's sort of forced on you with the huge superstructure of the rest of string theory. So there are lots of interrelated views on these ideas, and I'm only going to tell you about one of them, but the one that I feel is the deepest one. So there are the words associated with the ideas are that there's some tropical geometry, there's some fans in tropical geometry that I'll talk about. There's hyperbolic geometry. There's what I'll refer to as binary geometries that I'll tell you a little bit about. There's polytopes that are associated with all these objects. These are all connected to each other. But what seems to sit most primitively at the bottom of all of it is a certain counting problem that's naturally associated with the paths on this kinematic space. And this counting problem is very simple to define. I'll just tell you what it is without telling you exactly where it comes from. But the deeper origin of this counting problem has to do with the categories of quiver representations. And this is interesting because once you see these things in the more general setting, there are more general objects that have nothing to do with surfaces, that have nothing to do with the sort of standard things that we associate with either particles or strings that have the same important qualitative properties. And so there's various generalizations of what we think of as objects that carry the fingerprint of locality in spacetime and unitarity in quantum mechanics that we can actually see associated with these more general objects, which I think are going to be really fascinating to study. Okay, but let's just come back to Earth and talk about how we discover all the other diagrams and why we should add them all up. So let's come back and think about this very simple fact graph. Remember, this is corresponding to the disk with 5 marked points on the outside. So I'm drawing the fact graph now, and I'm just labeling for convenience the roads of this fact graph. So here, the road on the outside, I'm calling this one 1, 2, simply because it's bordered by this region 1 and region 2. I could just call them A, B, C, D, E. That's also fine, but I'm just calling them 1, 2, 2, 3, 3, 4, 4, 5, 5, 1. And these internal roads are 1, 3, and 1, 4. Okay, so let's say we now draw any old path that we can take on the surface, any route that we can traverse. So here's this one. This is what we were calling before 2, 5. Okay, but how would we describe this if we didn't know, if we weren't looking at it? Well, the way to describe it is to simply give the Google Navigate instructions for what the trip through the fact graph is. So the Google Navigate instructions are that you start on the road 2, 3, and then you make a left turn on the road 1, 3. So it'd be 2, 3, left 1, 3, right 1, 4, right 5, 1. Instead of drawing left and right, just for graphical convenience, I'm going to draw left as going up and right as going down. Okay, so every path through this fact graph corresponds to a certain word. Okay, so 2, 5 corresponds to this word, and I've recorded what all the words look like. And you see that obviously the ones on the outside, the ones that just correspond to boundaries, like 1 to 2, 2 to 3, 3 to 4. Here it's really simple, obviously, because it's a boundary. You're hugging the boundaries. You're turning left all the time. Okay, you're turning left all the time. Those are a little boring. But the ones on the inside can be more interesting. So the one from 1 to 3 goes from 1, 2 down to 1, 3 up to 3, 4, and so on and so forth. Okay, so we have 5, in this case, 5 interesting words. Okay, now all we're going to do is collect these words together, and the first thing to do is to just literally make vectors out of them. You can call these geometric vectors. That simply you choose a basis, which is a basis just of all the roads. Okay, so in this case, there's 7 roads in total. And then we just the geometric vector simply records the number of times a given internal road is traversed. That's it. So if I have a vector whose top 5 components are 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, and bottom components are 1, 3, and 1, 4, then this road 1, 3 would look like 1, 0, 1, 0, 0, 1, 0, just because 1, 2, 1, 3, and 3, 4 are visited once, and the rest are visited no times, and so on. Okay, so that's just it's completely trivial object. Okay, so I have this collection of geometric vectors. I have all these geometric vectors. I have geometric vectors for the boundary curves, and for these curves, I have 10 geometric vectors in total. There's a bunch of pointed vectors. They're all positive entries, positive integer entries. So there's nothing very exciting in this collection of vectors. But something exciting happens when I do the analog on this picture of putting the external particles on the mass shell when we think about a scattering process. The analog of putting external particles on the mass shell is to project through the geometric vectors that correspond to the external boundaries. So in other words, we literally want to sort of do a projection that sends those guys to the origin. And so in so doing, we're going to go from this 7-dimensional space to a 2-dimensional space. We're projecting through 5 directions. And so I can choose a basis, for example, for the geometric vectors of 1, 3, sorry, that should be 1, 4, and the rest of them. And then I can solve for 2, 4, 2, 5, and 3, 5, just that linear algebra. This is what I get. And the final answer in this 2-dimensional space after projecting is I have some, these vectors are now called G vectors. I have some G vector for 1, 3, some G vector for 1, 4, and then all the other G vectors are a linear combination of these guys. It's a very simple linear combination. And in fact, I stress this just to say that we're simply taking the geometric vectors as a completely obvious thing to do and projecting through the boundaries to get the picture of the G vectors. But once you know that's what you're doing, there's a shortcut to getting the G vectors, which you can directly read off from the word. This is very simple to derive. You just look at the word, and everywhere there's a peak, you record the peak with a minus sign, and everywhere there's a value, you record it with a plus sign. Okay, so here's the word for 1, 3, and so it just has 1, 3 in a value, so it's just plus 1, 3. Similarly, for 1, 4 is plus 1, 4, but for this guy is more interesting. I have minus 1, 3, plus 1, 4, and so on. All right, so now I've gone from simply recording all the curves. I project through the boundaries, and I have a 2-dimensional picture. I'm still just recording what all the curves look like, but now I'm just going to draw them. And this is where the first little miracle happens. If you draw them, now you see that this collection of vectors, of two-dimensional vectors, actually covers the entire space. Not only does it cover the entire space, but it breaks the space up into regions, into little cones. And if we see who bounds these cones, this is what they are. It's 1, 3, 1, 4, 2, 4, 2, 5, and 3, 5. And every one of these cones, if I now draw the corresponding chords, they correspond to a triangulation of the surface. They're a Feynman diagram. Okay, so here's a cone that's a Feynman diagram. Here's another cone, 1, 4, and 2, 4. Well, they don't intersect each other. They're a Feynman diagram. All of these are Feynman diagrams. In fact, these are all the Feynman diagrams. So what we've seen is that the cones correspond to triangulations of the surface that are Feynman diagrams, and they completely cover the entire space. Now, in a specific sense, they needed to be, they're naturally weighted by the same amount, because I can look at the area that's spanned by these vectors, and more generally look at the determinant of the g vectors in any given cone. And another remarkable fact is that the magnitude of those determinants are always plus or minus 1. So they all have unit volume. They have the same volume. So even though we started with one Feynman diagram, simply recording all the curves and projecting through the boundaries brings to life all the diagrams. They tile the entire space. There's a specific sense in which they have the same volume, so they should be counted by an equal amount. And this is the most primitive and basic sense in which space-time and quantum mechanics are just lying under our noses, simply in simple properties of the kinematic space. So I give you a very simple example from a surface that would correspond to a tree amplitude for 5 points. Here's another example that would correspond to a loop amplitude just with 2 external points that also illustrates what happens with spiraling curves and so on. I won't go through it in any detail, but you get an interesting looking fan again, and the fan once again covers the entire space and produces all the diagrams at the same time. Now, this fact turns out to be totally general. But of course, life is a lot more interesting. First of all, in general, the fan is infinite because we have infinitely many cones, and as I mentioned, we have infinitely many copies of all the diagrams. It's true that these cones cover almost the entire space. Almost. They miss certain lower codimension parts of the space. The very simplest example is that of the annulus here, where this is what the picture of this sort of the so-called G vector fan looks like. So these cones do indeed cover almost the entire space, but they miss all of them this final direction delta. And of course, it's no coincidence that that delta actually corresponds to a closed curve on the surface. And this is, in the language of just thinking about these geometric vectors and the G vectors, the avatar of a very famous fact in string theory, that even if you begin with open strings, you are inevitably forced to have closed strings in the theory. And in fact, if you pursue this a little more, you discover that if you want to cover the entire space, not just the top dimensional part, but also these lower dimensional holes, the real theory you're talking about is not this trace phi cube theory, but a trace phi cube theory as in addition to a single real scalar sigma that has its own cubic coupling sigma cubed and has a mixing with the scalar, with the colored scalar trace phi times sigma. So in a very precise sense, just the most basic sort of junior high school level combinatorics of drawing curves on the surface knows about the existence of the uncolored sector, the gravitational sector, starting with the colored or the Yang-Mills-like sector. The fact that all the cones and diagrams fit together is associated with a hidden symmetry that I don't have time to talk about now, but a symmetry that is hidden diagram by diagram, but is made manifest when you sum over all of them. That's all I'll say about the generalities. All right, now, so we've seen that simply recording all the diagrams, simply recording the data of all the curves and nothing else brings to life all the diagrams. And now this now inspires the following thought. We know that if I have any given one Feynman diagram, especially for these very simple scalar theories, and especially at loop level, although we could do it at tree level as well, that in order to, for example, perform the loop integrations, a very practical thing that people do is represent these diagrams in Schwinger parameterization. So that means that you take every propagator and you write it in this way. Here, I've for convenience done it so that things are Euclidean, but it doesn't matter. I could have put an I here and done it in a Lorentzian signature as well. Okay, and so for every internal propagator, you'd have a Schwinger parameter alpha, and you'd represent the propagators in this way. And this has the beauty that all the dependence on the loop variables is now Gaussian, so you can perform the loop integrations and get a Gaussian integral. And so you have to compute the determinant of some matrices and the inverse of some matrices, and this is a very standard thing. The loop integral associated with a given graph becomes an integral over an projectively an e-dimensional, where capital E is the number of edges of the graph, a simplex of an object that involves two famous polynomials that are known as the graph semantic polynomials. And the U graph semantic polynomials is the sum of all the ways of cutting the graph to a tree, of the product of all the alphas associated with the edges of cutting it that way. So this is all the spanning one trees. And the semantic F polynomials is the sum of all the ways of cutting the G into two trees, weighted by the momentum squared on one side of the tree or the other. So that's a story associated with a single graph. It's been well understood for a long time. And so what we're doing is representing a diagram, or even after loop integration, as an integral over a cone. Now, we can do it as an integral over the simple orthent, or of course I can do any linear transformation to write as an integral over any cone that I like. So given that we now know that all the diagrams fit together, each one of them looks like a little cone, and all these cones fit together into one giant object, it's now natural to see whether we can find a sort of unified form of Schwinger parameterization that would cover all the diagrams at once. So, for example, going back to this tree amplitude, I would want to somehow have a function that has for every curve on the surface its own private object, a little u sub x here, such that when I'm in this region, when I'm integrating in the space, when I'm in this region, only alpha for the curve 1, 3 and 1, 4 are non-zero, and there are linear functions that turn into the Schwinger parameterization for this diagram in this region. And then they would just move around. They would shift and move around, and different ones would be zero and non-zero in the different cones, but they would all turn into the Schwinger parameterization for the amplitude in the corresponding cones. Now, second thought says that it's very easy to do that. All we need to do is find some piecewise linear function, piecewise linear on this cone for every x, such that if you evaluate this piecewise linear function on the g vector for x over the g vector for y, you get delta xy. Then it's clear that if I now evaluate this entire action, which is just a sum of all of these x ux sub t, in any of these regions, they will just turn into the Schwinger parameterization for the corresponding diagram. Okay, so you can do that. You can do that for any old fan, whether it's this fan or any old kind of fan. You could define some notion of amplitude, some notion of unified Schwinger parameterization. And if you can do that, then we can again do all the loop integrals and be left with exactly the same kind of thing that we did before, except now instead of having these U and F polynomials associated with a given graph, they'd be associated with the entire surface. And these surface semantic polynomials have very simple definitions that, again, involve patterns of cutting the surface along chords, either to a disk or into a disks. So that's all fine. That's inspired by this idea that all the diagrams fit together. But very naively, finding this function that lights up one G vector is just as hard as enumerating all the Feynman diagrams. After all, we'd like to figure out, essentially, this is tantamount to knowing, if you give me a given vector in the space, which cone does it belong to? And well, you would naively think the only way to decide which cone it belongs to is to just go through all the cones and say, is it in this one? Is it in this one? Is it in this one? And so you'd have to just pass through all the cones, enumerate all of them, produce all of them, which is exactly the same as enumerating and producing all the Feynman diagrams to begin with. This is true of a generic fan, but something remarkable happens in this story. We'll find that exactly these functions, and this u sub x, the superscript t is going to is representing the fact that it's a tropicalization of a very simple set of ratios of polynomials. We'll find that these objects can actually be directly computed from a very simple counting problem associated with the word for x itself. I want to stress how remarkable this is, because what this is doing is knowing about all the different diagrams, knowing how things fit together, knowing which curves cross other curves, which are going to be compatible, which have a chance to produce Feynman diagrams or not. You would think that knowing all of that would not be the local property of just one curve at a time. Nonetheless, there's a function that you can build purely determined by a counting problem associated with a given word that knows about all of that. And so that's what I want to explain now. So, so here's the basic counting problem. Again, I'm just defining the counting problem a little bit out of the blue. In the story of quiver representation theory, these are very, very simple and canonical objects that count sub-representations of representations of a given sub-representations of given indecomposable representations of a quiver. But I haven't told you what the connection between the surfaces and quivers is, and I'm not going to have time to do so now. So I'll just give you just the direct definition of the counting problem, which is simple enough as is. So imagine you have any old word. So I've just given you here's some word. And now what we're gonna do is associate some generating function with this word, which is what I'll call the relationships with baggage generating function. This means that you can pick anyone here, but if you pick anyone, you must also pick everyone in their sort of past light cone in this 45-degree mountainscape picture. So that means that if I choose, if I have this word, then I can choose nothing, 1, or I can choose A. So that's simple. This is a slightly more interesting word. I can choose nothing, that's 1. I can choose A, that's A. But if I choose B, because A is in the past light cone of B, I also have to choose A. So it's 1 plus A plus BA. Here's a more interesting example. I can choose 1, I can choose nobody, I can choose A or D or A and D together. But if I choose B, I have to choose A as well. If I choose, I can choose B and A. I can also choose D. But if I choose C, I have to choose B and A, which are in this past light cone, as well as D in its past light cone, and so on. Okay. All right, so that's it. That's the counting problem associated with a given word. And then this is, again, a very simple, high school level recursion for it. If you want to figure out what this F polynomial is for a given word, you can just start on the left and decide whether or not the piece of the generating function you're including does or doesn't include the leftmost letter. And if you do that, just say that either it does or it doesn't include it, and you just divide things up into yes and no for including it and not including it, then there's a sort of a very trivial recursive way of relating F yes and F no for the bigger word to little f yes and little f no for the smaller word. That can be associated with matrices that go either up or down in this way. Okay, so this counting problem is then associated with very simple matrices m up and m down of y that depend on the variable in some particular spot on the curve. All right, so associated with this word, then we have some counting problem, and it's then very natural. We just take the product of all the matrices up and down associated with the word. We start always somewhere from a boundary. So the boundaries are not sort of part of the surface that we're talking about. So we're going to set the variable associated with them always equal to 1. But apart from that, we just take the product of all these matrices as we go. And so with every curve, you just get some product of 2 by 2 matrices, and you get some 2 by 2 matrix. Now, the determinant of all of these up and down matrices is just y. So the determinant of the product is the product of all the y's. And if we imagine that all the y's are positive, that's positivity makes an important appearance in this story in many ways. And here's the sort of simplest way that it occurs. Then the determinant of this big product of matrix is also positive. And so that means that AD is bigger than BC. So if we look at this nice ratio, BC over AD, that's going to be a variable that's bounded between 0 and 1. And these are remarkable objects. I'm going to tell you a little bit more about them in a moment. These are what we call them U variables. But for the purposes of what we're talking about, if we take these variables and they are now functions of these y's, they're going to be ratios of polynomials in y's. And if we now tropicalize these ratios of polynomials, and if you don't know what that is, I will explain it in a moment. then their tropicalizations are exactly the objects that we want. They're exactly the things that light up G vectors and precisely give us these global Schwinger parameters that let us write down the full amplitude. Now, in many ways, these U's are the biggest star of this entire show. In a different way of giving the talk, I could really have begun with this equation. And if I had to, in fact, if I had to tell someone to go to a desert island and reproduce everything I've worked on for the last 5 years from one clue, the clue that I would give them is this formula. That for any surface, we can write down this equation. For any curve on the surface, we have a variable u sub x, and there's the following beautiful equation that u sub x plus the product over all the other curves on the surface, uy, to the intersection number of x and y is equal to 1. It's very non-trivial that these equations have consistent solutions. In fact, they have a solution set which is exactly the dimensionality of the Teichmuller space associated with the surface. You can think of these u variables as defining a sort of algebraic compactification of the Teichmuller space. That's which is a counterpart to the compactification given by Fock and Goncharov and by surface cluster algebras, Fomin and Thurston. But it's completely algebraic characterization of this compactification, and it's a characterization that's absolutely crucial for making connection to a physics and allowing us to write this global Schwinger parameterization that defines all of the amplitudes. So now, if you now try to solve these U equations, you can try to do it. You can try to do it directly, and there's various interesting ways we found of trying to solve them directly. But there are two other ways of solving them by parameterizing their solution in terms of other auxiliary objects. One of them in terms of the lambda lengths and standard notions in hyperbolic geometry, and this also connects to Fock and Goncharov and the story of the surface cluster algebras. The other one is in terms of this counting problem that I told you about, which in many ways seems more primitive and basic. But in a sense, the equations themselves stand alone, and we may someday find even better ways of thinking about how to solve them and characterizing what their solutions look like. So again, they give a variety of the correct dimension. The solutions out of the equations give a variety of the correct dimension. If I do it in the simplest case at tree level, just for a disk, I just have the uij plus the product of all the kl of ukl equals 1. And why is this called binary geometry? It's because if we demand that the u's are positive, these equations also tell us that they have to be less than 1. But that means that if you sort of go to a boundary where some uij goes to 0, all of the u's that cross the chords go to 1. And so in a very binary way, we get a picture of compatibility. That the only u's that you bring to 0 together are things that don't intersect each other, and the maximal collection of those things are what we would associate with diagrams. And again, there's a binary realization for all surfaces, and this gives a global description of the compactification of a Teichmuller space, as I said, an algebraic one, as compared to the more local synthetic description given by Fock and Goncharov. Now, once you have these guys, you tropicalize them to get exactly the objects we want for the global Schwinger parameterization. Tropicalizing means that we imagine just going to infinity in these. Remember, the y's have got to be positive. So if we put y equals e to the minus t, we just have to go to infinity in one way or another in t space, and that'll either send y to 0 or infinity at various rates. So as u sub x as the y, if I replace y by e to the minus t, as t goes to infinity, this is just defined to be e to the tropicalization of u. And this simply picks the leading monomial that happens to dominate in any direction as you go out. So if we do this in the example of our 5-point tree, these are what the u variables end up looking like. You see very simple ratios of polynomials. You can verify that they satisfy those simple u equations. And tropicalizing them just means that as I go off to infinity, I set y13 to be e to the minus t13, y14 to the minus t14. So this simple polynomial, as I go to infinity, I just have to decide, is one biggest, y14 biggest, y14, y13 biggest. So this simply turns into the exponential of the max of 0 and minus t14 and minus t14 minus t13. And this is what we call the tropicalization of f. What's remarkable is that if we do that to these u's that, again, just came from this counting problem, the corresponding tropical functions do exactly what they needed to do. They light up on their ray and they kill all the other rays, and therefore they give us a picture of unified Schwinger parameters. Okay, so this allows us to write down, for example, a formula for tree amplitudes for all n, simply because it's very easy to work out what all the words look like. All the words are extremely simple. I pick a particularly simple triangulation like this one, or fact graph like this one, and the words are all trivial. These f polynomials are trivial. And again, just counting, the number of f polynomials is comparable to the number of chords, which is of order n squared. But the number of cones and diagrams that are generated by these piecewise linear functions is exponentially large. That's the magic. And we can then write an expression for the all loop amplitude. We just at any loop order also have to integrate over loop momenta and divide out by the action of this mapping class group. We know after we do the integral of the loop momenta, we're going to get these surface semantic polynomials, exactly as I mentioned before. They're all going to be functions of these global Schwinger parameters. And so we're simply left with an integral, again, projectivized here, with these global, surface semantic polynomials that depend on these global Schwinger parameters. All we have to do is mod out by the action of the mapping class group. And the standard way of modeling out by the action of the mapping class group that string theorists learn in textbooks is to identify fundamental domains. That gets harder and harder as you go to more and more complicated surface. But we took great inspiration from the work of Mirzakhani that provides an alternative way of modeling out by the mapping class group that's perfectly well suited to our story, where we essentially find an analog of the standard Faddeev-Popov trick familiar to a physicist. We insert a kernel, we insert one in an intelligent way following Mirzakhani. And so there's a kernel that you can insert into this integral over the entire space that affects the action of modeling out by the mapping class group, obviating the need to find a fundamental domain. Okay, so if we do this, we get the field theory amplitudes, and we get the field theory amplitudes written as an integral over a single space as a function of these surface polynomials that depend on these global Schwinger parameters. The magic is in the global Schwinger parameters. The global Schwinger parameters are remarkably determined in terms of this counting problem associated with each curve on the surface. If we don't tropicalize, if we keep the full the U's, we get essentially string amplitudes, and I put string in quotes. I won't have time to describe what I mean by that in more detail since I have to wrap up. But there's a number of things that are made obvious by this formalism. One of them is that if you understand what's going on at tree level for a large n number of particles, and also at loop level, just for even a single external leg, what physicists would call tadpole diagrams, all you've got to do is glue those things together in order to get expressions that are valid at L loops and N particles. So in other words, large N and large L have to sort of separately be solved, and then they can just be glued together to give you the answer for both large N and large L, something which is very much not manifest when you think standardly in terms of diagrams. And just to say these things, that they actually work. You can just do it on the computer. If you want to calculate the 4.2 loop amplitude in this theory, the leading non-planar correction, so something that looks like this with the topology of a torus. So there's that diagram and 419 more of them. Well, you get a 7-dimensional integral. You can just do it on Mathematica using n-integrate, nothing fancy, compared to what you get from summing over the diagrams directly, and numerically, they're pretty much on top of each other. Just to say quickly, to get string amplitudes, you just do what I said, exactly the same thing, except use the full U's rather than the tropical U's. And now comes the decision of whether you're going to take the product over all the curves or really all the curves, where really means curves that self-intersect each other, that self-intersect themselves. So if you don't include the self-intersecting curves, the self-intersecting curves are not needed for the field theory limit. But if you do want to, but you can include them. There's nothing wrong with including them. And if you do include them, that's a much more infinite product of curves. And starting at one loop, it's that extra infinity associated with the self-intersecting curves that ends up out of this formalism producing the things that look familiarly like Jacobi theta functions and other objects that are very familiar to string theorists looking at one loop amplitudes. But that's up to you. It's not necessary for the field theory limit. It might be necessary for some interesting things at high energies in a stringy sense, but it's not relevant for taking the field theory limit. All right, I think I've pretty much run out of time. I didn't have time to describe really the second part of this work. Maybe I'll just say something very briefly about it. So just to skip ahead to maybe the most interesting thing that we've learned, which is that everything I've told you about is about this very simple toy theory, this Trace Phi cube theory, at least my sense was that the one reason for studying this theory is that the pattern of singularities, the propagators, are universal for this color theory as for any other color theory of colored particles, including Yang-Mills theory. But that, of course, Yang-Mills theory is more complicated. The vertices in the Feynman rules have interesting numerators. There's different kinds of vertices. So we'd have to then sort of go back to the start and figure out how to incorporate all those vertices in some interesting way. And what's happened instead is much more surprising and interesting, that it turns out that this Trace Phi cube theory is actually sitting inside, the Yang-Mills theory is actually sitting inside this Trace Phi cube theory all along. I don't have time to well, I'll just sort of quickly say, you might think the most zeroth order question you would have is if you're going to describe gluons, the gluons have spin, the particles of spin 1, and so the standard way of incorporating the spin is to include polarization vectors. So where are those polarization vectors in this whole story? You just told me a story about scalars and just scalar propagators and no polarization vectors anywhere. Well, there's a very natural kind of scalar way of thinking about the polarization vectors. You really imagine that you plunk down the momenta of the particles, again, P1, P2, P3, P4, you get the sort of picture of an n-gon that closes on itself because of the conservation of momentum. But now you want to add the polarization vectors somewhere. And so here's the polarization vector for gluon 1, epsilon 1, and 2, and 3, and 4, and 5. Well, you're just going to put it here somewhere on 1 so you don't forget where it is, epsilon 1, epsilon 2, 3, and so on. But having done that, you now have a 2 n-gon. We call this a scaffolding picture, scaffolding the internal n gluons. And now you might complain, well, it's kind of random where you put the polarization vector. I could have put it anywhere, but it's trivial to see that if you move where you put the polarization vector, it's exactly the same as doing a standard gauge transformation on the polarization vector. So that freedom of where to put it is in fact reflected naturally in the gluon problem as a gauge transformation after all. And in fact, both the properties that the amplitudes we talk about have to be gauge invariant and have to be linear in each polarization vector are reflected in a very simple demand on the functions that I would associate with this 2 n-gon, a very simple affine symmetry that they have to have under shifting the kinematics in a simple linear way. So at least we can begin talking about gluon amplitudes in a scalar language. They have to be some functions with some special symmetry properties in order to be able to be consistently interpreted as having something to do with the gluons. So now, if you want to now ask where could we possibly get gluons from the top down, we would need to get some rationale to associate a function associated with the 2 n-gon that enjoys this interesting affine symmetry, in order to sort of discover where gluons would come from this point of view. And what's really remarkable is that exactly this question is just handed to us on a platter from this binary geometry. So if we go back to the picture that we were talking about, everything is determined by this parent graph, this parent fact graph. And now the scaffolding picture is just adding these little forks to the end of every road. So sort of doubling things by adding a fork to every road. Now, let's say that we take this new problem with the 2 n guys where I added the forks. If I wrote down the integral that we talked about before that defined the amplitudes, which was the integral of a d log of y, dy over y, times the product of all these x's, ux to the alpha prime x, that would give me the Trace Phi cube theory. What's remarkable is that if you simply replace the measure dy over y with dy over y squared, that actually gives us the gluon amplitudes. So simply shifting what I mean by these powers takes us from talking about scalars to talking about gluons. And in fact, it's literally a shift because the product of all the y's that occur in this expression can be shown to equal the product of all the u's with legs that are with even legs divided by odd legs, which in turn just corresponds to shifting these kinematic variables by +1 and -1 in these string units. And this very simple kinematic shift on the variables is taking us from the theory of gluons, sorry, from the simple scalar theory to the theory of gluons. In fact, you can show very easily from very simple facts about these U variables that the object that you would then define in this way exactly has those properties that are needed, those affine properties that are needed in order to be interpreted as actually coming from gluons. So this, I'm sure, went by way too fast to really digest, but I just wanted to give the idea of this really simple picture, that the spin of gluons is sort of incorporated by this doubling idea, just adding these polarization vectors and giving this scaffolding, that naturally takes us from a way of taking one triangulation mathematically to a bigger one where we just add forks on the outside. And once we do that, simply changing the measure from dy over y to dy over y squared takes us from talking about the theory of scalars to talking about the theory of gluons. This is still a conjecture, although I think we're pretty close to proving it. If you do this just in the simplest case at tree level, from this formalism, and then do some changes of variable to compare it to standard representations of string amplitudes, this really lands on a certain set of scalar, certain polarizations for gluon amplitudes in the bosonic string. But the lovely thing is that this now ports to any surface, and to higher surfaces is again our choice which curves to include, whether we want to include all the self-intersecting curves, none of the self-intersecting curves. This is all up to us. And it turns out that there's a very minimal choice that you have to make in order to actually get Yang-Mills theory out, which, unlike the case of Trace Phi cube theory, where you could get away with not choosing any self-intersecting curves at all, here, in order to get it to really look like gluons, you have to allow the curves to self-intersect once, or once per loop order. And there's interesting ways that the dependence on the space-time dimensionality comes in, also by including closed curves in a canonical way, but I don't have time to talk about it. But these are all they're conjectures, but they've really passed many non-trivial tests and more besides. So we're quite confident that they are right. All right, so that's really what I wanted to give you a flavor for, is that this simple scalar model does have a description for its amplitudes that's essentially completely combinatorial in terms of simple counting problems directly in the kinematic space that defines the order in the topological expansion that we're talking about for the amplitude. And second, that remarkably, these contain other interesting theories. And Yang-Mills is maybe the most interesting theory they contain. They also contain, by exactly the same kind of shift, simply not shifting by integers, but generic shifts, they contain the theory of pions at low energies, the nonlinear sigma model. So there's a sort of hidden connection between this Trace Phi cube theory, Yang-Mills theory, and the nonlinear sigma model that's made manifest by this combinatorial way of thinking about things. And in turn, this is associated with a number of hidden zeros and interesting factorization properties of these amplitudes that are completely unobvious in the Feynman diagrams and from any other formalism that we know of, but which are made very obvious by this sort of combinatorial fan geometric picture of what's going on. All right, so I'll just end by I'm sorry I've gone over time by saying that we're seeing more and more examples of fundamentally combinatorial and new mathematical structures that underlie the basic physics of space-time and quantum mechanics, at least in the case of elementary particle scattering processes, and a few increasing number of examples in cosmology. I'm most excited about the fact that my own sense in this business is that as we get closer to the real world, we have to see more magic, not less magic. because the real world should be the most magical thing there is. I think there are some people who have opposite attitudes, especially since some of the early indications for these kind of ideas were in the context of very special theories like maximally supersymmetric theories. There you could blame things on the supersymmetry or the integrability or the enormous well, anyway, all the stuff that we normally associate with these toy models. I think we can't do that anymore. Now we're really describing entirely non-supersymmetric theories, really things we see in the real world, the pions of the real world, the gluons of the real world. So I suspect that as we get closer to the real world, we see more and more magic, not less and less magic. A little bit more concretely, some frontiers. I mentioned early on that the sort of junior high school level understanding of this fan of these G vectors and the way they fit together and are associated with triangulations just forces something like gravity upon us. It forces the uncolored diagrams of an additional particle. And so that's definitely something that we want to understand much, much better. I suspect that this is going to be associated with a quite different, even stringy picture for what gravity is, that will not look like the sort of famous closed string equals open string squared, or gravity equals Yang-Mills squared, which has been a slogan in this subject, 30 years ago and 15 years ago and 10 years ago. That's a sort of by now very well-worn connection between gravity and Yang-Mills theory. I suspect there's something much deeper and more intrinsically gravitational about gravity that is exposed by the way it shows up in this fan, which looks nothing like the square of Yang-Mills or anything like that. And I would also say that as we get closer to the real world, probably the biggest open question is how to talk about the kind of gauge groups we actually see in the real world, which are theories like S23 cross S2 cross U1, but they have more interesting particle content. We have chiral fermions, and maybe the sort of cleanest way of thinking about approaching the real world is really to think about a grand unified version of the real world with the gauge group as SO10 with spitters. So how to think about geometrically about amplitudes in this way is even the most basic aspects of how to think about it. The analogs of the fact graphs and the simple combinatorics is something to understand. And finally, there's maybe the most obvious use for these unified tropical formulae for the amplitudes is to try to take the limit as the number of particles goes to infinity. This is a limit which I think has not been much studied when we think about amplitudes. But this picture suggests that as the number of particles goes to infinity, something very simple should happen. That these integrals over these unified spaces should turn into some kind of path integral, but with an action that has this piecewise linear tropical character to it. It won't look like standard free actions, but there's some kind of classical theory with the tropical action that should control the large number of particle limit of the amplitudes. And that's another obvious thing to think about next. And with that, I'll stop and thank you for your patience. Thank you.
Thanks, Nima. It's really an amazing talk. It's remarkable structures that you've discovered. It's late, but maybe we have time for a couple of questions.
Hi, Nima. Great talk. I'm curious, you started with a theory where phi was a matrix variable, and that led you right away into geometry lamination surfaces. But I was wondering, it's already hard to deal with Feynman diagrams when phi is a scalar. Can this machinery work there?
Yes. So that's what I was actually alluding to at the end. I mean, it's a very funny thing that the single scalar theory is actually harder to obviously associate with geometry than the colored one. And actually tell you very, very quickly, is that you, Dave, by the way? I just didn't. Oh, great. Yeah. Anyway, yeah. So it's very simple to describe why. I mean, if you have a colored diagram, even at 4 points, you have an S channel and a T channel. So there's only two singularities, and you can imagine associate the singularities with like two endpoints of some object or two rays of a fan. It's a one-dimensional space because you only have one propagator, and a one-dimensional space can at most have two boundaries. The problem is that at 4 points for just phi cubed with no color, you have all the diagrams, S, T, and U. So there are 3 singularities. You can't have in a one-dimensional space 3 boundaries. So that's the most basic problem. And it's related with another basic problem that that we're familiar with in string theory, that if I think about closed strings, the singularities for closed string amplitudes occur in real codimension 2. So if I have the 4 points on the sphere, it's in real codimension 2 where they bubble off like that with a long thin tube connecting them, not codimension 1. It's a feature of open strings that we see things in codimension 1. So somehow all of this story that simply connects amplitudes and geometry, part of the 0th order connection is that the singularities of amplitudes are associated with facets or boundaries of geometries. But this is missing this most basic gravitational thing that goes down in 2s. However, having said all of that, I mentioned at the end that all the diagrams for exactly the theory you're talking about, as well as their interactions with this color theory, are there in the fan. They're there in this crazy fan, but they're there in a kind of crazy way. If I had longer, I would tell you. I mean, the action of the mapping class group is very heavy in this case. Even if you want to describe the 4-point, phi cubed model, the exactly one that you're talking about, to do it, you would be led to a 2-dimensional space where every ray in this 2-dimensional space, every rational direction, would be associated with either an S or copy of an S or a T or a U channel up to some Dane twist. And it's only the action of the mapping class group modding out by the mapping class group that tells you to select only 1 ray for S, 1 ray for T, and 1 ray for U. So that looks, to begin with, like a hard way of thinking about just a very, very, very simple process. But I suspect that we have to get used to thinking about it, figure out how to do it more systematically, that'll give us a new way of thinking about that simplest, what appears like the simplest theory.
If I understood, you're saying that graphs are a stepping stone to dealing with ordinary graphs.
Yes, I think so. I think so.
Thank you.
Okay, thanks. Well, it's getting a bit late. I mean, it's just fascinating. There's so much more that we could ask you, but we look forward to hearing more another time.
I really hope to visit again soon. It's a wonderful place, and I'm very sorry again I couldn't be there for this fantastic event.
Well, thank you. Let's thank Nima again.
Thank you.